Hello. Today, in this video lecture, we will see this numericals on Euler's theory. This is last chapter of this strength of material subject, and chapter name is axially and eccentricity loaded columns. First, read this numerical and understand this numerical. An alloy tube, 25 mm internal diameter. That means this is an alloy tube. An internal diameter is 25 mm. And 40 mm external diameter. So this external diameter 40 mm. When subjected to axial tensile force of 60 kN, undergoes an extension of 3.84 mm over its 3-meter length. So that means this is like this. Actual length is 3 meter. Actual length, that means total length. And it is subjected to axial tensile force. 60 kN axial tensile force. And the problem statement is, what is shape axial load resisting capacity? So shape axial load resisting capacity we will find. And let's see boundary condition. When one end is fixed and other end is hinged. So here let's consider this end as fixed, and let's draw here line diagram. This end as fixed and this end as pinned, and factor of safety to be taken as 4. So this all is given data, and we will find shape axial load resisting capacity. So how to solve this numerical? First, understand we know Euler's formula, and with the help of Euler's formula we will find buckling load PC buckling load. And for this buckling load, see in this numerical they had given us factor of safety to be taken as 4. So when this buckling load will come, just divide this buckling load by that 4, then you will get that shape load. So first we know that buckling load formula is PC is equal to pi square EI upon L square. And you all know that, like, how to find this LE. LE depends upon boundary condition, and see here boundary condition is one end is fixed and other end is pinned. So for that boundary condition, effective length is like this, and this effective length is nothing but the LE is equal to L by root 2. So this LE we will find by using this equation. LE is equal to L by root 2. This L is nothing but the actual length, and this is actual length is 3 meter. So this is clear. This I, moment of inertia. How we will find moment of inertia? See, this is like hollow circle, hollow alloy tube. That means this portion is hollow. And we all know that moment of inertia for x-axis and y axis for that circle is same, like I is equal to pi d raised to 4 by 64. But here this portion is deducted, that's why we need to like minus pi small d raised to 4 by 64. This capital D is 40 mm and small d is 25 mm. So as per this, we will find this moment of inertia, this LE. So, and when this PC comes like X value, then just for shape load, this PC X value divided by 4, you will get that shape load. So just find this. Okay. First we will find effective length. LE is equal to L by root 2. For boundary condition, one end fixed and other end free. So this effective length is depend on that boundary conditions. For different boundary conditions, it will be different. So this L, we know that L is 3 meter. So in mm it is 3000 divided by root 2. So 3000 divided by root 2. 2121.32 mm. Just see crippling load formula. What we need, then just get that terms. This I we need. So I is nothing but the moment of inertia. And see, for design we are interested in to consider least moment of inertia, but you know that for the I told you already that for circular shape moment of inertia along x and y directions same, so no need to calculate both moment of inertia. Just calculate one pi outer diameter raised to 4. Outer diameter is 40 mm. 40 raised to 4 pi d raised to 4 divided by 64 and minus inner diameter pi. Inner diameter of that circle is 25 mm. So find this moment of inertia. Pi into 40 raised to 4 divided by 64 minus pi into 25 raised to 4 divided by 64. It is 106488.94 mm raised to 4. That means 106.49 into 10 raised to 3 mm raised to 4. Okay. So this IELE complete. Now find this E. So E is nothing but the modulus of elasticity. And just remember our first chapter. Just remember that chapter name. What is that chapter name? Simple stresses and strains. And you know that E is nothing but the stress upon strain within proportional limit, and stress is nothing but the load upon area, and strain is nothing but the change in length upon original length. So do some mathematics, you will get this PL upon A delta L. You have that P, C, axial load, tensile load 60 kilonewton. You have that L is that 3 meter. A you have that circular shape, so A is nothing big deal for you. So A and delta L. So let's find A. A is pi by pi d raised, what is A? Area of circle, pi d raised to pi d square by 4. So pi by 4 into d square, but this is hollow tube, that's why d square minus small d square. 40 25. 40 square minus 25 square. So this area is pi by 4 into it is 765.76 square. Okay, and the delta L is also given quantity in numerical. See this delta L, this they had given us. I read it. This delta L is extension of 3.84 That means this is delta L. So P is 60 kilonewton. So convert this into Newton. 60 into 10 raised to 3 Newton. L is 3 meter. That means 3000 mm. This A is 765.76 and delta L is 3.84. So this E 16 this E is 61213.69. And unit of E, see this here, just directly calculate with the help of that formula. This is in Newton, this is in mm, this is in square, and this is in So get cancelled. This unit is Newton per square. E unit, modulus of elasticity unit. So just put all that, see this E, this I and this LE, that three are required for this PC formula, and pi square is constant. So just put this all like terms in this PC formula. So PC is equal to pi square E. E is this 61213.69. Pi square E I, moment of inertia is 106.49 into 10 raised to 3. Pi square EI upon LE square. LE is this 2121.32. So calculate it. Pi square 6121.3.69 into 106.49 into 10 raised to 3 divided by 2121.32. So it is, and see this formula. Our LE is 2121.32. And see this formula, LE square. So here we need to put square. So square of that term is pi square 6.1. Again see, this is 106.49 into 10 raised to 3 I, moment of inertia. Okay, 6121.63. Let's calculate it by the help of calci. Pi square into 61213.69 into 106.49 into 10 raised to 3 divided by 2121.32 square. So it is 14296.99. And unit, just calculate this unit. This is constant, so, and this is in see Newton per mm square. Newton per mm square. This is in mm raised to 4. This is in mm. So this mm raised to 4 cancel. This is mm cube. This mm square cancel. So remaining is only mm. And see this square. So this is square. So this mm also get cancelled. So unit is Newton. And in kilonewton it is 14.296 kilonewton. And I told you that shape load is nothing but the PC upon factor of safety. And factor of safety they had given us in numerical, it is 4. So PC is 14.296 upon 4. 14.296 upon 4, it is 3.574 kilonewton. It is like shape load. What is its shape axial load resisting capacity? So shape axial load resisting capacity is 3.574 kilonewton for factor of safety 4. And remember, I also told you that this formula is also in our chapter 1. So in our chapter 1 we had seen that factor of safety. I told you that see factor of safety for brittle material. The definition, just remember that definition. The ratio of the ultimate stress to the working stress for a brittle material is called as factor of safety. So here ultimate stress to the working stress. Just by that way we had see here also FOS is equal to PC upon SAP. So just concept is similar. Factor of safety is equal to buckling load upon SAP load. So by that way we had calculated it, SAP load. And I also told you for like ductile material, factor of safety for ductile it is like yield stress upon working stress. Remember that for ductile, factor of safety is up to yield stress upon working stress, and for brittle it is ultimate stress upon working stress. So by that way we had solved this numerical. So See, just length, geometry, length of that column, geometry of that column, and see, they had given us load also, boundary conditions. So with the help of formulas and all this, we are able to solve this numerical. So thank you very much.